Hi guys, Mr. T again. I'm in a secret location today, just basically in an office closet, making this video. And today we are going to be talking about graphing polynomial functions. Okay, and it says an essential question being, how do you sketch the graph of a polynomial function in intercept form? Well, we're going to go past that eventually, but right now we're talking about an intercept form, and what we're going to do is we're going to use the attributes. So we're going to look into the qualities, the characteristics of these kind of graphs and be able to use those so we can sketch the graph. Okay. So first we're going to spend a good bit of time just really talking about polynomials. What are they and what are their attributes? And then we're going to turn around and be able to use them to graph. Okay. So what is a polynomial? So let's look at this next slide here. Okay, and here are several examples of polynomials. Okay, and so we got the first column here. Those are linear. Okay, and so those are linear functions. And then you got quadratics in our second column. Okay, um, and then you got cubics, and then you got quartics in our fourth column. But polynomial is kind of a general term for all of these and more, right? X to the fourth and so on, and x to the fifth, x to the seventh. Okay, polynomials, just many monomials here. And so this everything here would fall under polynomials. Now, we're mostly not going to focus on lines and quadratics in this concept because we've moved past that. But that doesn't mean we're going to forget about them. What we've learned about linear functions and quadratic functions, we're going to use those to do everything else pretty much. So it's not brand new stuff. It's all the same kind of deal. Okay, so let's start off by just kind of looking at these families here. Now, the way I've got these situated here in the classroom, I got them all lined up on the wall, but the reflections on them were just terrible, so the camera just didn't pick them up well. So we put them up here, and I think this is going to be good for us. And you see that along the top here are the parent functions, okay? And it's just a term we use for the basic simple function, okay? So in this first column, this is linear, and you notice that all of them have an x to the first power. But this one is just real basic, no extra pluses or minuses. And then over here, we have x squared, and it doesn't say x squared plus something or minus something or times something. Whereas these guys have x squared minus something, and this one's negative x squared plus 4x. So those are what you call the, quote, children of the parent. And it kind of makes sense as we try to talk about that, is that do they look exactly like the parent? No. But are they similar? Yes. Okay. And so that's pretty easy to see for the first couple here. And then cubics are pretty much the same deal. These quote children look very similar to this one. Now, when you get to the quartic, the thing polynomial to the fourth power here, it gets a little crazier. But the higher the degree, the higher the exponent, the more craziness that can happen. It gets more interesting for sure. And so, but you notice that each one of these are still going to be similar. This is just super basic. And sometimes people, kind of don't understand, why is this not got another little twist or turn? Well, because it's all just x to the fourth. It's just one straight. And it looks very similar to the quadratic, but you notice something here. The quadratic is a little wider and pointier. But with the quartic, it's a little straighter up and a little squattier, right? A little wider at the bottom, less like a V, more like an actual U, because a lot of times we talk about parabola being U-shaped, but it's really, really not. This x to the fourth is more U-shaped, actually, but that's okay. So that's the beginning of those, looking at those guys, reminding ourselves what is a parent function. Okay, so let's look across here and what a parent function in children kind of look like. That's just terminology to help us describe these different groups. All right, so the first thing here, these all have x to the first power. Okay, so that is a first degree polynomial. First degree polynomial, the highest exponent is 1. So, okay, and then this is x squared. The highest exponent is 2. So the degree of each of these is 2. So that's a second degree polynomial. Okay. And you should write these terms down. And several of these terms have two different terms you can use that are interchangeable. And you need to write these little terms down as we go along so you can refer to them until you get used to using them and hearing them. And you're going to like, now what was that term again? Well, write it down so you can remember it, okay? And you can keep referring back to it until then you don't, at some point you won't need to because you'll remember it. But have that handy till then. So this second one's a second degree polynomial. This third one has the highest exponent of 3, right? And so it's a third degree. And this is a fourth degree polynomial, okay? Another term for degree, instead of degree, they use the word order. So this would be the order of this polynomial would be 1. Order of this function would be 2. The order of this function would be 3. The order of this would be 4. It's not as common of a term used. Degree is the main term we use. However, it is a term that is used, and it's specifically used with a particular app that we like to use on the TI-84. Okay, so why is the degree so important to know? Well, it's a pretty huge deal, actually. Okay, because if you'll notice on the first degree, how many times it crossed the x-axis? 1 time. On the second degree, how many times can it cross? 2. Okay, sometimes it doesn't cross at all, but sometimes just 1 point. But always the most it can do is 2. Okay, and we'll come back to that. And then cubic. Well, this one's only crossing once. Well, that's 3. That's touching twice. That's touching once. But the most it can do is what? 3. Okay, and then this is a quartic. It's a fourth degree. So if I pulled that middle piece up, I could cross 4 times, couldn't it? Okay, so what the issue is this: the degree tells you how many zeros or solutions, answers that you have. Now, we learned with quadratics that you always have 2 solutions, but you're saying, excuse me, that's only touching once. Well, what happens is you get the 0 twice, so you get it's called a repeated solution. You had to get it twice, okay? This one would be imaginary solutions, so you still get 2, and then this one would be 2 real solutions. Okay, so the degree tells you how many solutions. Well, the degree also tells you something else. If you'll notice, this is the first degree, and this is a third degree. So that's odd, right? The odd degrees point up and down, don't they? They point up and down. There we go. Don't we see it? Up and down. Odd degrees. Even degrees, either both up or both down. Both up or both down. So the degree is also very helpful to what's called end behaviors. Where are the arrows doing? At the end of what we can draw, what's happening at the end? So odds are always going up and down, opposite directions, and evens are going both up or both down at the endpoints. So degree is also important for that, okay? Well, how would I know if they're going both up or both down? Well, let's look at this one here. This is a positive in front, and they're both up. The next one here, they're both up, and look what's in front, a positive. Oh, and a negative in front does what? Makes it go down. That's not new information. We learned that with lines, didn't we? A positive slope, a negative slope. So a negative in front is making it go down, okay? So whether that's downhill or just double down with your arrows, right? Now, but what about these cubics? Well, just think about this. If I drew a line from one endpoint to the other, wouldn't that be going uphill? Yeah. If I drew a line from one endpoint to the other here, that'd be going downhill, just like that negative in front. So these are some of the characteristics we see in polynomials that we can use to our advantage, okay? And then lastly here, we get this fourth, which is an even degree, and we notice that positive goes up, negative, oh, they both go down, positive, they both go up. This is a really strange one. But the higher the degree, the more interesting things happen. Okay, so we've talked about degree, we've talked about order, talked about the number of solutions always matches the degree, even if you have to go into the imaginary world or repeat the same answer. Turning points. Okay, let's look at that. Turning points. Well, how many? This is a first degree. How many times does it turn? 0. So a first degree has 0 turning points. Okay. Second degree. How many times does it turn? So a second degree has what? 1 turning point. So a second degree has 1 turning point. So a first degree has no turning points, and a second degree has 1 turning point. So it's 1 less. Is that a pattern? Okay, well, let's look at this. How about a third degree? Okay, well, this first one doesn't have a turning point. That's actually just a swerve. Okay, it doesn't go straight through, but it also doesn't turn. So I'm going to call that a swerve or a point of inflection. Okay, I'm just call it kind of swerve, kind of, I'm going to turn, sight, not really. Okay, kind of deal. But look at this. Oh, this is a third degree, and how many turns does it have? 2. So a third degree can have 2 turns. It doesn't have to take all of them, just like it doesn't necessarily cross the x-axis 3 times, but it can't have any more than 2. And just kind of think of it. So this is an example of 0 turns with a cubic. This one has, so it's a third degree with 2 turns. Okay. Could you have a third degree that has 1 turn? No, because if you have a third degree with 1 turn, you know what they call that? We call that a parabola. So that wouldn't be a third degree at all, would it? It'd be a second degree. Okay, so that wouldn't really account. So this one has, so generally what you think of is it's the number of turns is 1 less than the degree at maximum. It doesn't have to do it that many times, but at most. So like this guy here, it has 1, 2, 3 turns. And then it's got 1, 2, 3, and a fourth degree. So fourth degree has at most 3 turns, always 1 less. So that's turning points. Now, there's a couple of other important words. Okay, they're called maximum, minimum. Well, we've already talked about that, right? With the parabola, we did that. We said this is the minimum of that function, and we said this vertex here would be the minimum, or that'd be where you'd find the y value, which is the minimum. And then over here, this vertex is what the y value of the vertex, because that's the function value, would be the maximum, right? Well, we're going to add to that. We're going to add a word in front of that. Okay, we're going to add 2 things. We're going to call something the absolutely smallest number or the absolutely biggest number. Okay, and so we call that the absolute or global minimum, or the absolute or global maximum. Those are 2 interchangeable words to describe these. Okay, so this point right here, this spot, there's absolutely nothing smaller than that. So that's the absolute minimum, or the global, absolutely nothing bigger than the globe, right? In concept, right there. Then this guy down here, well, that's the absolute minimum, global minimum. Again, these are words that are important. If you're following our current textbook, I think it's page 251. It's got a lot of highlighted words in there. This is the words we're talking about. Then this is an absolute or global maximum. Now let's slide over here to this cubic right here, because there's no turns here, so there's no max or min on the parent function. But down here, see this spot here? That looks like a maximum to me, right? Isn't that the highest spot right there? Well, it's called a local or relative, because in this neighborhood right here, around that area, it's the tallest point, isn't it? But is there a taller point on the graph? Sure. See, this thing goes up forever, doesn't it? So what happens is an odd degree will never have an absolute or global max or min, because you got arrows going up and down. So when you got arrows going up and down, you're never going to have an absolute global max or min. You can have locals though. You can say, well, if we only look at this little area right here, that's tall. If we only look in this little area right here, that's small, right? That's a minimum. So we call that a local or relative minimum, a local like is in the local area or relatively maximum. Okay, so let's look at the parent function for the cortex. So this has an absolute minimum, doesn't it? That y value right there is the absolutely lowest spot up and down that you can go. Now let's look at this turning point. Is that the absolutely lowest spot you can go on this graph? Yes, it is. You can't go any lower than that. So that is a global minimum. Okay, what about this spot here? Is that the absolutely tallest thing that you can find? No, this has got arrows going up. So it's not absolutely an absolute maximum, but it is a relative maximum. Because that for that relative area right there, it is the maximum. Okay. Well, what about this guy down here? So if this one on the left is the global minimum, what about this one on the right? Because you can only have one absolute minimum, right? That's the whole point of absolutely, right? There's only one of them, but there's two. Actually, that's not true at all. That's not true at all. Remember, we talked about the minimum value being the y value. The y value. Doesn't both of those locations have exactly the same y value? So since they have the same y value, they have the same minimum value. So yes, that's the same minimum value, the absolute minimum. However, it occurs in two different spots for x. So that's, again, we've been talking a lot about the difference between a point and a value. So that's the spot you find the minimum, okay? Or those are the places you find the minimum. But what you find out is the y value for both of those are exactly the same, and that is the minimum function value, the y value. And we've talked about that quite a few times. Okay, let's look at one last little issue when it talks about max and mins. Okay, this guy here, this little spot right here, is that absolutely the tallest? Mm-mm. But it is a relative for that area or a local maximum. This area over here, that is a local minimum. But what about this guy here? Is that just local? No, that's an absolute maximum. There's no point, there's no y value, that is, there's no spot with a y value taller than that on this graph. So that's an absolute maximum, relative minimum, and a relative maximum. All right, so that's a lot of terms to throw at you. A lot of terms to throw at you. Got one more thing I need to throw at you, though. Very important. Everything you see here, every single one of these equations, is written in standard form. In standard form. None of these are written in what's called intercept form. Now, intercept form is more often commonly called factored form. Okay, so if I were to factor these down to, monomials or binomials kind of thing, so the factors would be called the intercept form because we can find the intercepts real easily using that. Okay, so what does that look like? See, like this right here, where it says like a number, x minus a number, x minus a number. This is called the intercept form. It looks a lot like factors because they are factors. Okay. So, but the official term is intercept form, and I think you'll see that a little bit more. Oh my goodness gracious, I almost forgot. So we got to go back one more time right here. I want to look at these four graphs and look at how they cross the x-axis. So at x to the first power went straight through. Okay. What happened to the x squared? It came to the x-axis and said, never mind, and bounced off. Okay. We call that a tangent point where a curve touches a straight line in one spot. That's a point of tangency, but that looks kind of like a bounce, right? So we're saying if you have an x to the first, you're just going to go right through. If you have an x squared, you're going to bounce. Okay. If you have just a plain old, right? What about x to the third? Is that a straight through or a bounce? No, it's a swerve. Okay, it's a swerve. So x to the third is going to give you a swerve when you cross the x-axis. and then an x to the fourth. Oh, that's a bounce as well. That's also a point of tangency. Okay, that's also a bounce. Okay, so so if you have an even exponent, you're going to end up getting a bounce when we do this sketching thing. Well, that doesn't make complete sense right now, but it is good. Make those notes. Okay, that x to the first is going to be a straight through. If you have a exponent that is even, you're going to get a bounce or a tangent. If you have a third power, you're going to have a swerve. Okay, and we'll see how that flies here in just a little bit later. Okay, now we're ready to jump over here. So we've gone through all of these terms. We talked about the intercept form, talking about turning points, tangency here, our global and absolute max and mins, lots of these things right through here. All very important stuff. You can go through and read all that for detail if you want to. Just kind of pause it and read through that if you want to look at the details of that. But that sets us up for this little chart to kind of walk through here. So as we're going to look at these characteristics of a cubic even closer. Okay, so the first thing here we see that we got three different functions. All three are cubics. All three are cubics. Okay, so if I multiply, so this is x to the third. If I multiply these two, that would give me x to the third. Well, if I multiply this stuff out, I don't know what the rest of it would be, but I know that I would get an x to the third eventually. So I can look at these guys, and by the way, this here, this is intercept form. This is intercept form as well. Okay. You say it looks like it's factored to me. Well, it's the same thing, remember? They're the same thing. Okay, so here we go. And it says, first thing it says distinct factors. Well, looks like there's one distinct factor three times for that one. This one's got two. We got three here. One, two, three distinct factors. Okay. Okay. This has got one distinct three times, right? And this has got two distinct, but one of them is repeated. Okay. Now it says, what are the graph's x-intercepts? Well, another word for x-intercepts are the zeros. So what's that mean? What numbers can I plug in for x to make it equal to 0? So what can I plug in for this first function to make it equal to 0? 0. Okay. What about these guys? Well, I could plug a 0 in for x squared. That'd make it 0. But what could I do here for this x minus 2? Well, if I put x minus 2 equal to 0 and I added 2 to both sides, I would get x equals 2. Yeah, 2 minus 2 is 0. Okay, so that would give me two zeros. And the same thing for our last ones. So 0, 0, or 2 would make it 0, 0, 2, or negative 2 would make that 0 because the x-intercepts are also known as the zeros of the function. Okay, now you kind of see where it's called the intercept form because you can easily look at this guy right here and figure out what the x-intercepts are very easily. That's why it's called the intercept form. Okay, now let's look at this next group here. It says, is the graph tangent to the axis? That means, does it touch the axis or does it cross the axis? Well, this is just the parent function at x cubed, right? So it's going to cross the x-axis, but does it just cross it straight through? No, it does a much fancier way than that, right? And so I'm going to add something to this dude. I'm going to actually say, hey, not only does it cross right there, it swerves. Swerve. It's going to swerve as it crosses. All right, that's the parent function. Okay, now this guy at 0, it's got that square. And what did we say about the squares? That gets a bounce. So it says tangent, but I'm going to say bounce. Right? And then this guy here, that's to the first power. That's going to be just straight crossing through. And then all of these, okay? So go back to this idea that I showed you on the previous page. We looked at this, okay? When we go to look at these graphs, we're looking at it's either going to go straight through, it's going to bounce, or swerve. And again, bounce, which is the same as that. Those are our choices. And so, depending on what kind of exponent we have, that's how we know what's going to happen. So, these are all to the first power. So, they're going to go straight through. Straight through. That one's going to bounce, and this one swerves. And so, you see where these words are coming from. Okay, so, let's jump on down here. Turning points. Okay, we talked about that previously. This one doesn't have any. This guy has two. This one has two. I guess now would be a good time to kind of show you what those things look like. So here's my graphing calculator. I got just this first one looking at here. So remember, there's your parent function. So now I'm going to come down and turn that dude on. Let's take a look at that. See, there's the bounce, and then there's the through, the red one. Let's come back over here, and let's turn this next one on. See, I just gone over to the y equals, hit enter, and now when I hit graph, you can see it too. And see, look, it went through -2, through 0, and +2, just like it says right there. And so, and you can also see the number of turns. Okay. And then lastly here, grab this guy and just slide it way over there. Okay. So this has no, it talks about the global max and the local max, global min and local min. Well, the parent function has on the cubic has no turns, right? It just has a swerve. So it has no max and mins at all because you got to have a turning point for that. Whereas these guys, there is a local maximum and local minimum for each one of those. Okay. So that's all good there. So take a minute to look at that a little bit more later. All right. So okay, now to the fourth power. It's a very similar thing. See if I can't speed up this process a little bit. So distinct, there's one here, two distinct factors, three distinct factors, and 1, 2, 3, 4. See, I'm hiding the fourth one there. So there's four distinct factors there. What are the x-intercepts? Well, that would be 0, 0, and +2. Again, that's what would make it 0. 0 to -2, 0 to -2, and -3. And that's what that says right there. And you can double check that. Again, this is where it's going to cross the x-axis. And it's also the numbers you can plug in to make the thing equal 0. So the same thing. Now it's looking for tangency, okay, or bounces, where it touches or crosses. Okay. Well, see here, this is x to the fourth. It says tangent. So remember, what kind of words did we use for tangent? We used the word bounce, didn't we? We used the word bounce. Tangent's the official math term. That's fine. And then x to the third, it says crosses at both ones. But guess what? What's going to happen here? That is going to be a swerve. It's not only going to cross, but it's also going to be a swerve at the 0. Okay. Then this guy here, what's going to happen? It says tangent. Again, that's a bounce. And then crosses at these other two. Since those are x to the first power, it's going to be straight crosses. And all these are going to be just straight up crossing the way. Okay. So how many turning points? Remember, it's always got to be at least one less. Okay. And we can look at these graphs and we see that happens there. That's not as big of an issue for the deal. And then we talk about global max and mins and such as that. So let's take a second and look at those graphs. So let's go back over here and we'll turn that off, turn that off, turn that off, turn that on. Let's go look at the graph. This goes so fast on the computer. And so you see there's the parent function. Okay. Here's our first one. And we said that's going to have a swerve and a through, right? And a swerve and a through. So there, see, there's the swerve at 0 and then a through at the 2. Okay. And what do we notice? This is a absolute minimum. And since this is a swerve, it's neither, there is no maximum relative or not, okay? And then we're gonna go back over here, and okay, this square, that's gonna be another bounce and a through and a through, okay? And so that's gonna cause what? 3 turns this time? And this is 2 turns? Interesting how that works, huh? So there's your through, there's the bounce at 0, like we talked about, the x squared, and then through here. And then one more, the last one, see what that looks like as well. See, the higher the exponent, these polynomials get very interesting graphs. Very, very interesting looking graphs. And then there's craziness there. But again, we have a through, a through, a through, and a through. And you notice that all of them end going up, don't they? All of them end going up because why? These are all positives in front, right? So it's an even degree. So it means it has to be both up or both down. And since it's positive in front, they're both up. Okay. So, all right. So these are some attributes that we've talked about. We've talked about all these different things, these turning points, the degree, and all these things you can know. There's a lot of stuff going on here. Okay. And then we've studied the cubic and the quartic, just get an idea of some more details about them. So let's do 3 examples. We're almost at the end. I'm going to do 3 examples of where all this stuff pays off, okay? So the first thing we're going to figure out here is what is the degree? Okay, well, we did one earlier like this, and we said x times x times x will eventually be x to the third. So the degree is a 3, okay? Now that's important because it's odd, which means what? You're going to have one up and one down, right? And so since it's odd and it's positive in front, that means it's going to kind of go like that, right? So what's going to happen here is it's going to be kind of like that. So it's going to kind of do something in the middle, then go up like that. Okay, so that's the first thing we need to figure out is what our end behaviors are going to do. What's going to happen at the ends. Next thing is what are our zeros. Now you could put this first or second, second and first, that doesn't matter. But these are the 2 things we got to do before we go any further, is get our end behaviors and our x-intercepts. So we got 0, -2, and +3, because those are what would make those 0, the x-intercepts. So let me transfer this information over here. Let me put this down arrow over here. As soon as we get this circle, not stopping going around. So we got a down arrow there and up arrow here. So all this stuff is pretty straightforward. Okay, we got a third degree, so we got to have an up and down, and it's got to go uphill. We know it's going to go through those points. Okay, last thing before we go any further, we need to check. When it goes through these points, is it going to go through? Is it going to swerve? Or is it going to bounce? Okay, well, all of these are x to the first. So these are real simple start off. They're all going to go straight through. But this is what I always got to be thinking. So let me go. So the red is what's pretty straightforward, got to happen. And now I just got to play connect the dot. Okay, so here we go. I'm going to start over here. So, and then I'm moving towards this first dot. Now think, do I go through, swerve, or bounce? And this is a through, right? So I'm going to go through. Here I go, went through it. Now I got to go through another point. Where is it? Oh, there it is down there. So where do I turn? Since we're sketching, don't care. Anywhere you want to. You can go way up or just a little bit up or just medium. It doesn't matter. Okay, for our sketch purposes. Okay, we're going to go through here again because all these are to the first power. Looking for my next dot. Where is it? Oh, it's over there. So I'm turning around, heading back towards that next dot. And then again, this is a through, not a swerve or a bounce. Can go straight through that intercept. And then, oh, looky there. Finished my sketch. No big deal. Okay. So all of these things that we've talked about are coming together so that we can make this happen. So let's look at a couple more examples. Okay. Now I know I've thrown a whole lot at you here, but hopefully a bunch of it was review just with some new terms. Okay, let's look at this guy. Again, first thing I want to do is say, what is my degree? Well, my degree is a 4 because it's 1, 2, 3, 4. So if I multiply that out, I get x to the 4th eventually. Degree is a 4, okay? Oh, and check this out. What's that negative doing here? So because of the negative, and so we know for degree 4 it's going to be both up or both down. So is it going to be both up or down? Well, this negative tells me that they're going to be both down, right? So this is a down. Reminds me down. So it's going to be, I mean, I don't know what's going to happen all here, whatever, right? But it's going to be both down, okay? So then I got my x-intercepts. So we got one at 4, right? Positive 1. Okay, that's positive 1 plus minus 1 be 0. Then negative 1, and then negative 2. Okay, those are my zeros, my x-intercepts. Okay, so we don't do negative 4. We're plugging in. What can we plug in to make it equal to 0? Because that's what the y equals on the axis. Okay, so we got our x-intercepts, and let's transfer our end behavior. That's what that's called, our end behavior. Okay, these are the things that we know for sure that aren't really hard to figure out. Okay, if it's 4th degree, both up or down, it's negative, so both down. X-intercepts. Okay, now do we have any squares or cubes? Okay, no squares or cubes, so everything again is going to be straight through, no swerving, no bouncing. Okay, so we're still just doing real basic. So here we go. We're going to start. Let's go connect the dots. Okay, there's our first dot. Go through it. Where's our next one? Oh, it's down there. So we got to turn around and go back down there. Going to go through it again. No bouncing in this case. Where's my next dot? Oh, yeah, there it is over there. So I got to turn around, go see it. There it is. So again, I'm going through because there aren't any squares or cubes. Going through. Okay, this is nice. Where's my next one? Oh, it's over there. I'm looking for my next place to go. And again, there's no bounce or swerve, so we're going straight through. And look, we're going straight to that other arrow. Okay, what happens if you don't land like this? Well, a couple of things have happened. Either you put your arrows in the wrong place, or you put your intercepts in the wrong place. But oftentimes, if you're getting good at that, you bounced when you shouldn't have bounced, or you went through when you should have bounced. That's usually where that's going to be a mistake. And practice will help that. So let's do one more practice problem. Okay. So here we go. Okay, now what kind of degree is this? Okay, the degree of this guy, well, since it's going to be a 3, because x squared times x is going to be would be x to the 3rd. So the degree, okay, that's 3. All right, and then what's going on next? Well, that negative in front, what's that going to do? So is it because the negative front is going to be downhill, right? So this is not just down, it's downhill. Okay, so that means it's going to kind of look like this. Some stuff in the middle, whatever, right? Something like that. So now let's go to our x-intercepts, which are going to be 0, so x squared, and then positive 4. Okay, now bring over our arrows, our end behavior, what that's called. Now, before we get started, what I like to do is go double check. Ooh, I see a square. So what's a square going to do? It's going to be tangent or a bounce. So I'm going to highlight this little dude right here so that when I get close to that thing, I know I need to bounce. Okay. Um, if you're just using a pencil, you might do a light circle. You don't have to, but it sure does help us when we're drawing our thing. And then this one's going to be a straight through. So, okay, let's go back to change my color. So let's start from the left. So I'm heading towards my next point. I see that it's going to be a bounce. So I'm going to go touch it and bounce off. Okay, where's my next dot? Oh, there it is, heading towards my next dot. And as I'm approaching it, I ask myself a question. Is this a through, a swerve, or a bounce? And this is going to be a straight through because it's x to the first, and there we go. We landed. Easy enough. So it's downhill because we got a negative in front. Okay, we got two turns, and we got a tangent or a bounce, and at these 2 points, we did good. Okay, I know that's a whole lot again, guys, as we've been talking about this idea of graphing polynomial functions, how to sketch the graph using in intercept form, using all these characteristics, these attributes of polynomials. But you get a lot, you can get some more practice at this, and you'll be surprised how easy this is going to be, as long as you just got to keep all the pieces together. Okay, hope that is helpful. Talk to you later.